Good morning and welcome to the last lecture in the series on fault tolerant control and the last lecture of the course. So today we are talking about some recent advances in adaptive methods for fault tolerant control. So we are providing some motivations for using adaptive fault tolerant control methods, and in particular presenting one approach called Subspace Predictive Fault Tolerant Control. And finally, we will provide some references and pointers to other techniques that you may want to explore further by yourself. So first of all, we already presented in previous lectures some technique for fault tolerant control that were based on so-called active approaches. So approaches where you have a fault diagnosis step telling you which fault happened, and based on the knowledge of which fault happened, you know how to explicitly design a controller that is accommodating that fault. And we said that on the other side of the spectrum, we have instead passive approaches, for instance, approaches based on adaptive methods. And so the question is, why do we need these other kind of approaches? So we are trying to provide motivations for that. So if you recall, the block diagram for active approaches is this one. So you have your plant, and you have first one block that is diagnosing and detecting whether you have a fault, which fault you have, and how big it is that. So you identify and estimate your fault, and the results of these are these two variables, so a decision of whether you have a fault or not and which one, and an estimation of the size of the fault. And they are used by another block, a supervisor block, whose role is to redesign the controller or switch between a number of pre-computed controller such that you can accommodate that fault. So this is how active fault tolerant control was working. Instead, in a passive approach, such as the adaptive fault tolerant control approaches we are talking about today, you take out the diagnoser and you have a simpler block diagram where data from the plant, so input and output of the plant, are continuously used by a learning law in order to tune the controller. So the role of the learning law is similar to the role of the supervisor, that is to tune the controller. But here, you don't need to explicitly know whether you have a fault or not. The learning law is constantly updating the controller to adapt to the dynamics of the plant, be they healthy or be they faulty. So this is completely transparent. It is continuously doing its job, so it is just working by itself. From this point of view, it is passive. So you don't need any active decision whether to start accommodating the fault. So whether you have some normal and physiological wear out of the plant, so aging of the plant, or you have a fault, no matter what, this is adapting. And the goal of that, of course, is to have performances track some desired value. So there are many ways to implement that. So if you followed some courses on adaptive control, you know that you have direct and indirect adaptive control methods. But you have also other approaches like having a controller that has a polynomial function of a wavelet network that you tune based on data online, or similarly, you can have a controller based on a neural network that you tune online using backpropagation or gradient descent. And this is actually similar to what we have seen in lecture 5.4 for learning an unknown fault. Or you can also use other kind of more, let's say, modern machine learning approaches like reinforcement learning, active inference, and you name it. You have a lot of choices, and the common ground in these approaches is that they are continuously tuned online. So then what are going to be the shortcomings of active approaches and how passive approaches like adaptive fault tolerant control can overcome them? Well, the thing is that in active approaches, you need an explicit FDI decision and fault estimation, which means that you need to know what are your faults. So the fault classes, the knowledge base needs to be designed by experts. It's not something that you can easily and automatically build. And having a fault diagnosis block is also adding computational complexity. But most of all, here, you need a model. And having a good model is something that is costing. It's costing time of an expert and is requiring a lot of data. So if you can do without a model, this is an advantage. And indeed, passive adaptive approaches, usually, they don't need a model, which indeed is a big advantage. And also, they have less computational complexity because you don't need the FDI step. Well, this is maybe debatable because they are also adding complexity in another aspect, because the learning law itself can add complexity. But anyway, you don't need this step. And most of all, they also work always both in healthy and in faulty conditions. So the learning law is continuously adapting your controller in order to be the optimal one for that condition. Anyway, as I pointed out before, the distinction can sometimes be blurry, because as we have seen in lecture 5.4, we can also have active approaches with an FDI block where the FDI block is adaptive. So when we shown how to learn an unknown fault, that was indeed using an adaptive function inside the observer. So sometimes it is not just black and white. So let us now go a bit much deeper in details and present one adaptive approach. And this is called the Subspace Predictive Fault Tolerant Control approach. This approach is based on three components. So you take data from your plant, and the first component, the first step that you have is a subspace identification block. So this block is continuously learning a model of the plant. So now it might seem tricky because we said these methods do not need a model. So the fact is that they internally need a model, but the model is automatically identified from the plant. So you don't need an expert designing that model. So you just need data and this algorithm. This indeed will identify online a model that is used here in this second step to build an output predictor. So the role of this one is to predict what the plant is going to do over a time window in the future. And using this information, you can design a controller. So if you look into that, you see that you have a sort of model predictive controller. Indeed, this is what we are going to design later. So as you don't need explicit knowledge of the model, you are learning that from data. This approach is called a model-free or data-driven approach. So just to give a brief glimpse of why this is going to work and why this is going to be fault tolerant. So imagine that at some point you have a fault which is affecting the plant. We draw it like this. So as soon as the plant becomes faulty, data that is coming here will reflect the faulty behavior. So after some time, the model that you learn here will no longer be the model of the healthy system, but will be the model of the faulty system. And when the model of the faulty system is used here, the controller that is designed is a controller that is tuned to that faulty behavior. So one thing that I want to stress, everything that is happening here is happening online at every time step. So the controller design that you see here is not something that you do it once. It's something that at each time step is repeated. So you have this flow of data coming from the plant, you identify your model, you update your output predictor. This is producing prediction of the behavior of the plant in the future that is used to design the controller. Then, next time step, everything is repeated. And so this is why this is fault tolerant, because as soon as you sample some data from the faulty behavior, this is updated and it is matching the faulty system. Of course, there are some kind of faults that you can adapt and some others that you cannot adapt to. So let us imagine the case where all the sensors fail. I mean, this is an extreme case. But when all the sensors fail, clearly, there is no way to identify a model because you have no information. So this is going to work for faults that are not so big to completely destroy information. So this is quite an intuitive point. And later we will see how this translates mathematically. But anyway, this is the limitation of adaptive approaches, as we also pointed out in previous lectures. In order to implement that, we need to assume a form of the equations of the system. I mean, the equations of the model that we are learning here. And the assumption is to have this linear system in innovation form. So you see usual terms here. The only novel part is here, the term E. So E is zero mean white noise, that is also called innovation. Anyway, we write this, but we don't know yet the values of these matrices. So we are not assuming that we know this model. We just assume that a model is in this form is suited to represent the dynamics of the plant. And the goal of the first step, so the goal of the subspace identification we have here is to identify these matrices A, B, C, and K. Or actually, to identify this matrix here, phi, which is equal to A minus KC. And one assumption that we need is that the plant is such that the matrix phi that we get is stable and the system is minimal. So we can only identify systems that fulfill this assumption. How to do that? So in order to do that, we need to write the output of that system in this form. And when we write it in this form, we get an input-output description of the system we had before. So the output of this model is just written here in this way. So what are these new symbols that we introduce? So first of all, we have YT, which is the matrix of the output data. This is a matrix that you build by taking measurements of Y over different time steps, so over a time window, and you stack them together. So you have Y at time t, Y at time t plus 1 until Y at time t plus n minus 1. So we index this matrix capital Y with the index t at which we start collecting this data. And this is something that we know, we can measure from the system. Another thing that we know and we can measure from the system is this matrix calligraphic Z, which is defined in the next slides. Is quite cumbersome to write, but similar to this one is a matrix built by taking measurements that we have from the input and the output of the system, so U and Y, and stacking things together. So these are things that we know, but there are also things that we don't know. So one is the matrix X. So the matrix X, similar to this one, is obtained by stacking columns, not of the output, but of initial states at some time t minus s up to t minus s plus n minus 1. Okay, well, a lot of indexes over time. But anyway, these are the effects of the initial states on the dynamics of the system, on the output signal. And this is something that we don't know. We don't know because there is no way to directly measure the state, of course. We can only measure directly the output. Similarly, past noise data is something that we don't know. We don't measure it. So this is adding as uncertainty in this equation. Finally, the last symbol that we have here is the matrix capital Xi, which is the matrix of the Markov parameters. So this is the thing that we want to solve for. This is the thing that we want to identify. And indeed, it contains matrices, terms of matrices of the model. So we have here C and then the power S minus 1 of phi that multiplies B, the same that multiplies K, up to C phi to the power 1 that multiplies B, and similar that multiplies K. So you see here C, phi, and B, and K. So the matrices that we had here. So you may wonder how we came up with this description, but actually this is just another way of writing a convolution sum. So for a slightly simpler linear system whose dynamics is written like this, x at time k plus 1 equal a x k plus b u at time k, and y at time k is equal to c that multiply x at time k. So let us consider this linear system. So if you want to write the solution for the output of that, you can write a convolution sum. That is, you know that y at time k is equal to the matrix C that multiplies two terms. One is A to the power of k minus some k0 that multiplies initial condition at that k0 plus, and then you have a summation over an index h going from k0 to k of what? A at the power k minus 1 minus h that multiplies matrix B that multiplies the input u at index h. And we close the square bracket here. So you may have seen these in courses on systems theory or digital signal processing. So if you think about this convolution sum, so this explicit way of writing the output as a function of initial states and the input, and you think about these, well, they are equivalent. So this is just a way of writing this convolution sum. So you see that we have here C, this matrix to the power of something, and then initial states. So this is equivalent to this first part that you have here. And then the Markov parameters has terms that are exactly equivalent to terms that you have here. C that multiplies A at some power that multiplies B. So here it is slightly different because we also have terms multiplying k. But if you stick to this simpler form, then this is completely equivalent. And here in the data matrix Z, you will see that we have terms that depend on past values of U. So this is just a way to write in matrix form the convolution sum that is in a summation form. And shouldn't come too much as a surprise, because indeed here we have sums of products. And a matrix product is indeed computing sums of products. So if you can just build a big matrix with all the terms that you need beforehand, then you can write this summation as this matrix product here. So that's equivalent. So once that you see that, this shouldn't be so much a difficult equation to understand. Anyway, you just need now to see how we define this matrix Z, so how we prepared all the terms that we have in the summation. So the matrix is written in this way. So you have past values of the input. You also have past values of the output. So you just need to try yourself, if you want, to expand the equation we had before using this definition of the matrix, and you will see that indeed you get the convolution sum that you need. Anyway, once we defined the data matrix in this way, what we have here is a linear equation. A linear equation in the data we know and in the parameters that we need to estimate. So you see here we have the term we need to solve for. Here we have the data that we know. And here we have noise. So such kind of problem, estimating these from a noise equation, basically, is something that you can solve efficiently using a method that you know very well, the least squares method. So indeed, a solution to estimating the Markov parameters matrix is to compute this least squares solution. And what you have here is the data matrix YT of the output data that multiplies the pseudo inverse of the data matrix Z, the one with all these other terms. So remember that this plus here means the pseudo inverse. And now you see in a mathematical way what I meant before when I said that data we have from the system should be informative enough. So data coming out of here cannot be just all zero or just data that is redundant. So you have n copies of the same sensor. The way to see that is by looking here and remembering that to compute a pseudo inverse, you still need to compute a matrix inversion. If that matrix has a determinant equal to 0, you cannot compute its inverse. And so this is the way to see that mathematically. If you had all the output equal to 0, then this matrix, you cannot compute its pseudo inverse. Okay, so now that we have a way to identify online the model, well, one thing I want to stress about the online. So please look at the time indexes that you have here, and also the time indexes that you have here. So the data you are using is on a time window that for the output is from t to t plus n minus 1. And here data is from t minus s to t plus n minus 2. So basically, if you have a plot here, you have some time t. You have your first data matrix here from t to t plus n minus 1, t plus n minus 1. And these other data metrics, we said, is from t minus s to basically the same, but here you have a minus 2. So you need to think about this algorithm as an algorithm that is at every time step recomputing its solution. So at every time step you get a new estimate of this one, and the estimate that you get here is computed using data that you collected over these 2 time windows, and they of course they move over time. So if you have a fault here, initially you cannot estimate a new model that is taking into account that fault. You need to wait for these 2 windows to move forward in time and cover data that is faulty. So as we have seen previously in the lectures on change detection, there is a trade-off between how good is your model. So the longer these models, so the longer these time windows, the better you are estimating your model, basically. But also, the longer will take you to react to an abrupt change in the dynamics of the system. So if you want to be able to react to a fault in, let's say, 10 time samples, then this should be no longer than 10 time samples. But then maybe the model you can estimate is not that much good. So you have this trade-off. Okay, once you have that model, anyway, you can use it to predict also future outputs of your system. And these will be needed to implement predictive type controllers. The way to predict the output for time instance from a time index k to a k plus f is to implement this equation, which is, again, a linear equation in terms that we know, because here we have a matrix that is obtained by concatenating terms like this one, which are based on the matrices we just identified, and multiplying it by another data matrix. So this is notated differently than the previous Z, because this is actually defined differently. So this new Z is obtained by staking just over a column u and y from time instance from k minus s to k minus 1. So we are also using a different time index, k instead of t, to make it easier to understand that the prediction is another step with respect to the identification. And here you have this big matrix that again has terms based on the Markov parameters we identified that is multiplying these data that we have here, u and y from time index k to k plus f minus 1. And then finally, what we have is a term that depends on initial states. So the thing that we said we don't know. So actually, in this form, we would not be able to compute it because we don't have direct measurement of this one. But luckily, there is a lemma that we will not prove, so you can find the details in this paper here. But this lemma is providing us a form of the prediction of the output over the next time window that we can actually implement, because now here we only have terms that we know how to compute. So look back at this one. So here we had y over time window k to k plus f, depending on things in the past. So that likely we know, we measured. Depending on things in the past that we don't know, so the state, but also depending on things in the future, including the output itself. So this is not something that we can directly compute. If we want to predict what is y in the future, so at some time k plus f, how can we require to know the output? So it's ill posed, of course. But anyway, this is a way just to show that this is going to approximate the output. But in order to compute a prediction of the output using only data that we know, likely we can use this lemma. So indeed, what you have here, you have, let's make a drawing. So this lemma is telling us that at some time, okay, you can predict what is going to be y over a time window from k to some point in the future. This is k plus f. Using what? Using data that you collected over a time window in the past. So from some k minus s to k. And using values of the input u from time k to k plus f minus 1. So this is again in the future, but the good thing is, so we have here the u, here the y hat that we want to predict, and here we have the z over bar. So the thing that makes this equation useful and computable is that from a control design point of view, the input u in the future is something that I know because I'm computing it. So if we implement a model predictive control, u over a time window in the future is something that indeed is solved for by the controller. And the controller can use this predictor actually to predict the output that you will get using that input sequence, and then optimize the controller to match some cost function. We will see the details in the future. But the important thing is that this is something that you can compute by using data you measure in the past, and what you know is going to be the input to the system in the future. Okay, so how can we use this to get a fault tolerant control law? Well, if you assume that a fault is occurring at some time t0, as we said previously, as soon as you get enough data in your time windows after t0, and you can identify the faulty dynamics, and then the control law that you design based on that is matching the faulty dynamics. So let's try to draw this again. So at some point we have a fault. At the time that we have a fault, we still are using time windows in the past, so previous, so before the fault, in order to predict things after the fault. So I'm trying to make the same drawing as before. So we had this z over bar, and we also had the calligraphic z, but I'm not drawing that here, otherwise it's not clear. So we have the z over bar, we have the sequence of input we're going to apply in the future, and we have the sequence of outputs we are going to predict in the future. So when we are exactly at t0, we are using data in the past and control actions in the future of the fault, but they are compute based again on data in the past. So at this time, we are not yet able to compensate for the fault because the model we are identifying from data is from data before the fault, so it is still a model representing the healthy system. So the controller we are going to design at this time, and so the input sequence we compute at this time, is still something that is working for a healthy system. But as long as these things are moving forward in time, then we can adapt. So let us redraw these. So let us assume that now we moved enough forward in time such that the entire time window for the matrix Z over bar is past the fault. And so here we have the time window of the U we compute for the future and the time window of the Y we predict in the future. So if you remember the indexing we had, this is k minus s to k. So when we are at time t0 plus s, finally, all the time window that we use for identifying the model and designing the controller is past the fault time. So when we get to this time instant, we identify a model using only faulty data. So this is a model representing the faulty dynamics, and so the controller and then the control action we compute here is accommodating the fault. But I will want to stress one time again, the adaptive approach is going to introduce a delay in the way you accommodate the fault, because you need these S time steps before your time windows are all past the fault. So again, you have this compromise. So you want S to be long in order to identify a good model, but you want it to be short in order to react quickly to a fault. So, and if this fault is something catastrophic, so that is leading in a short time to failure, then an approach like that maybe is not the best. So again, we have different methods. We have active and passive approaches. We need to be careful when we decide to implement one or the other, because they have different pros and cons. And one of the cons of the adaptive approach is it takes time to adapt. In the meanwhile, your system can explode. For mild faults, instead, this is perfectly fine. Okay, but now we need the final step. So we thought about designing a controller that is using predictions in order to compute the control action over a time window and the future. How we do that? So we mentioned model predictive control as a natural way to address the framework we just built. And indeed, we are presenting an example based on that. One thing that we need to know in order to implement our model predictive controller is the future reference. So a signal R from time k plus 1 to k plus f that is telling us what is the reference that the output of the system needs to follow. But this is something that likely we know, because we know the reference that the system needs to follow. Then we need to define a cost function. So a model predictive controller is optimal in the sense of minimizing a cost function. The cost function that we define is this. We have two norms here. So we have a difference between the reference and the predicted output. And then we have a change in the control signal, delta U. This is the input change. And we want to minimize that over the future time window from k plus 1 to k plus half. And you see here that the norms here are indexed by Q. So these are matrix-induced norms where you have these two weighting matrices, Q and R, that are positive definite. So from this point of view, this is the usual cost function for an LQR controller that we already know. So the difference in this case is we have a reference to follow. So in order to solve the problem, we need to introduce a couple of auxiliary matrices just for convenience of writing things down. So we introduce these two structural matrices where this IM here, they are identity, and this 0 here, they are null blocks. So you build these block matrices of 0 and 1s such that you can write the input change in the future, delta U, as this S delta that multiplies U in the future minus this S K minus 1, this other one, that multiplies the data matrix Z over bar. I mean, this is just some technical trick to write things in a simple form. Anyway, once you do that, we can introduce this problem, this optimization problem, whose solution is the sequence of inputs in the future, the sequence that the controller is computing. So as you can imagine, this problem is telling that we want to minimize the cost function that we introduce it. Over what? Over all the possible sequences of future inputs. And this problem has a closed form analytical solution. So this is something that we can do because we have linear dynamics and we have no constraints. And so we can get this closed form analytical solution. And you see that here you have only terms that you know. So you have terms including the weighting matrices, the structure auxiliary matrices, the sequence of references that we know, and the data in the past that we know. So everything here is known. So you can explicitly, directly compute this U star. And if you remember how model predictive works, this is going to be computed at every time k, and the solution is valid for the future time window from k to k plus f minus 1. But at every time step, you are applying just the first element of this sequence U star. And then at the next time step, you compute that again, and you again apply just the first element, and on and on and on. So this is like playing chess. So every time that is your turn to move, so you think what is going to be the best course of action over the future, and of course you can implement just the first move. And then it is the turn of your adversary, and then it is your turn again. In our case, the adversary are all the uncertainties that we have occurring to the system, so the effect of the noise E, for instance, but also they are due to possible faults that are altering the dynamics of the system. And as it takes time for us to adapt, then it makes even more sense that we just apply the first element here that is the most up-to-date, let's say. So what are the benefits and limitations of this approach of subspace predictive fault tolerant control? Well, as we said, as it is a passive approach, we don't need an FDI block. And also, it is always working, so you don't need separate control schemes for healthy and faulty situations. This is just working. It is some way passively adapting to what the plant is doing and continuously producing a control action U that is optimal. Optimally in the sense of the cost function J that we define. Be it healthy, be it faulty. Of course, faulty cannot be so much faulty that we completely lose control authority or we completely lose sensor. But if the fault is mild from this point of view, this just works. And also, we are not limited to one control law, we can have many. We can have LQR, MPC, techniques based on linear parameter varying models, and so on and so on. The only thing that you need is a way for this control design law to be tuned based on that model that we learned. So if you have a control design law that can be used with a model in this form, then it is fine. So what are the limitations? Well, the first and foremost limitation is that there is no guarantee of closed loop stability, which for a control system is regrettable, to say the least. I mean, there is no theoretical guarantee. But anyway, in practice, it works. But the issue is quite pressing, because let us look at the scheme again. So you have a scheme where you have two loops, so the control and the plant, and then the control, the plant, identification, output predictor, and control design law. And even if the controller is stable, it's a different story to guarantee that all this is stable, because the controller is continuously updated. So who is going to tell you that this loop here is not going to explode and make the gain of this controller go to infinity? So this is the question. This is the added complexity of having an adaptive control where the controller itself can change at every time step. So proving stability in the general case is not yet solved. For some specific cases, it is. Still, in practice, this is working well. And then the other limitation is the one that we already stressed many times. So these can be slower than an active approach to adapt to a fault. And so if you have an abrupt fault that is very dangerous because can lead to failure in a very short time, maybe this is not suited as an approach. One thing that you can do is to have a sort of hybrid approach where you still have an FDI block and you still have your adaptive part, but when the FDI block is detecting that you had an abrupt fault of one of the kind that you know is really dangerous, then you immediately switch the adaptive part to some pre-learned controller that you know is good for that specific, very dangerous fault. So for that case, you don't wait to learn. You immediately switch to a controller that can accommodate that fault. For everything else, you have enough time to learn. So this is a way to get the best from both worlds in terms of performances, but you're also getting the worst in terms of computational complexity. So again, a trade-off that can be good for some applications and will not be worth for others. So here we see an example of applying this to a wind turbine. So wind turbine where as inputs you have collective pitch angles and generator torque. So I invite you to read the papers or look back at some of the material presented by Dr. Liu on how a wind turbine works, but I want just to refresh here that the pitch angles of the blades can be controlled, and the torque of the generator can be controlled. What we measure as outputs is the speed of the generator and the power produced by the generator. So you want to match some speed. You don't want to overspeed your turbine, otherwise it will explode, literally explode. But you also want to track some power that the grid operator is asking the turbine to provide. So in order to do that, you can do two things. So you can increase the torque of the generator, which will slow down the turbine, or you can alter the pitch angle of the blades. So you can pitch the blades in a way that for a given wind speed, you get more torque such that the turbine will accelerate, or you can pitch them in a way that the mechanical torque is less, and then the turbine will slow down. So these are the two inputs that you can control. So in order to apply that, you need to get data from the wind turbine and run the subspace identification step, and then the model predictive or another control step. So we're not presenting the details here. You can look at these two papers, but we are just showing some results where we have a fault, an abrupt fault happening here, and that's a drop in the hydraulic pressure of the pitch actuators. So you are no longer able to change the pitch angles of the blades as you want it to. You assume that the wind speed over the simulation that you have here, so this is simulated data, is doing this. So you see some random behavior of wind speed, which is something you see also in practice. And we have three controllers that we are comparing. One is a simple PI controller that has no fault tolerant control capabilities. And then we have two, where we have the subspace predictive fault tolerant control we shown, and then an improved version of that. So what you see is, before the fault, all the three controllers are behaving pretty much the same, and the pitch angle and the generator speed, they are some way smooth, even if you have disturbances, because of the wind speed is not constant. But after the fault, you start to have oscillations. So because of the fault, it is more difficult for the turbine to track desired speed and generator power. But the oscillations for the simple PI controller are much bigger than the oscillations for the two fault tolerant control, as you would imagine. So the two fault tolerant controllers are able to damp these oscillations. And you see that they need some time. So initially they are not so good because they are still learning the faulty dynamics. But after a while, you see the black and the red line, they are behaving much better. You see the same also here. And if you look at the red and the black line is some way better than the red. But for the full details, I invite you to have a look at the papers that you have here. Okay, so finally, I would like to present a list of relevant papers on different approaches that we were not able to cover. But still, if you are interested in the topic, I invite you to read. So on the topic of subspace predictive fault tolerant control, there are some papers, some we already referenced, that you can look at. For other approaches, I have a short list of papers that are mixing adaptive and switching approaches that are considering linear or non-linear dynamics. I have some papers that are using neural network approximators in order to learn online the dynamics of the fault and compensate that. And I have also some papers about applications with machine learning approaches to fault tolerant control. So this is one paper using reinforcement learning, and this is one paper that, disclaimer, I co-authored on using active inference. Active inference is an approach inspired by neuroscience theories, and it explains that in terms of a tendency of our brain to minimize surprises. So if you go back to this scheme, you see that here we have data from the real world, and we are using that to make a model, and this model is altering the way we interact with the real world. So in the active inference approach, it is assumed that the brain is doing something similar. So the brain is creating a model of how reality works, and then it is minimizing surprises between what the model says and what reality says. So after you learn this model of reality, when you get new sensory data, your brain doesn't like when this new sensory data is different from what the internal model is saying. And this surprise is quantified using a quantity called free energy. And so what happens that when this surprise is too big, the brain is going to change the way it is interacting with reality in order to minimize surprises. So for instance, if you are walking and you're used to walk in a certain way, and maybe you get injured or there is something on the floor, you alter the way you're walking in order to compensate that and minimize your surprise about how do you expect yourself to move forward. So if you are interested in these, let's say, novel approaches that are less based on control system theory and more based on machine learning, well, then I invite you to have a look here, definitely. Okay, it's time now for a short recap. So today we presented an introduction to passive adaptive fault tolerant control schemes, and in particular, we covered subspace predictive fault tolerant control. And we presented some bibliography, some references over other approaches. So this is the end of the course. So the only thing that is left now in the next weeks is the final exam on January 21st. Thank you.